So in the last lecture, we were talking about Ohm's law, right? And we presented Ohm's law in its field form. So this is the current density, conduction current density, right? And it equals the conductivity times the electrostatic fields. So different materials have different conductivities. I want to show you now. I'm gonna show you some tables from the text. Oh, this is a table of different materials with different conductivity constants, and it shows you like the difference in conductivity between conductors and insulators, right? So you can see like silver is very conductive at 6.1 times 10 to the power 7 Siemens per meter. And we said Siemens is amp per volt, right? Copper is only slightly less conductive. Gold, aluminum, sometimes because aluminum is so light and cheap, like for some transmission lines, actually a lot of transmission lines are aluminum. I don't know what other materials are common for transmission lines, but most of the transmission line conductors are aluminum because they are light and cheap. And you can see carbon is 2 orders of magnitude less conductive than copper, 100 times less conductive than copper, but it is nevertheless still a conductor. Right? You have when you go to insulator, you see how conductivity starts dropping. So for example, wood is 15 orders of magnitude less conductive than copper. Polystyrene, I think it's a kind of plastic. It's a whopping 23 orders of magnitude less conductive, right, than copper. Right? Now here, this shows the conductivity of different kinds of semiconductor materials. So you can see semiconductors are kind of in between. They're not as isolating as insulators, and they're not as conductive as conductors. Like they're in between. So they have values that, right? So this is gallium, antimony. I think silicon is there. And then some biological materials. Okay. Seawater is slightly more is 4 times more conductive. Well, it's tons of times more conductive than water, right? Conductivity of water is 1/10 to the minus 3, while seawater is 4, and the reason is because of the ions, the positive and negative ions of the salts that are dissolved in the seawater. Okay. Then interesting thing about silicon is that although it is not very conductive in its pure form, you can dope silicon with either N-type molecules, atoms, or P-type, right? So you could example dope silicon with I believe boron or phosphor to change the conductivity of the material. Okay, so we said this is Ohm's law. Ohm's law, as if you remember it from circuits, is you would encounter it in circuits in its lumped form, V equals IR, and I said that form is equivalent, right? So what is R? What would R be in this case? Right. So let's tie in Ohm's Ohm's law in its field form to Ohm's law in its circuit form by evaluating R using the field variables. So R would be V over I, right? So assume we have some kind of cylindrical material. It's always easiest to assume a cylindrical structure in the direction of the flow of the current, right? So I have a length L here. I start from point A and end at point B. Then I have an electric field in the conductor that's causing the current. So I have some E in the field, some E in the material, and then I have some J in the material due to that E. So R is V over I. What's V? V is the assuming we have a voltage across the material, VAB, right? This is point A and this is point B. So VAB over I. So what would VAB be? It's the voltage from the voltage difference between A and B is the voltage that we get if we take a test charge and move it from point B to point A, right? So VAB is essentially minus the integral from B to A of E dot dl divided by the current, and the current using the field variable J is just the total current is just the surface integral. So this is the surface here, the size of the cylinder, surface integral of J dot ds, right? So yeah, so this would be the, I think in my notation this should be V. If I have VAB, I should have something like, oh yeah, no, this makes sense. So VAB is the voltage that I get if I start at B and move to A. So the end point is the first parameter point, and the start point is the second parameter. So I'm going from B and ending at A. Either way, we should get a positive value here because the resistance is positive, right? So this is equal, what's the voltage? Well, I mean, the assumption is that the electric field is uniform, so I end up with EL, the length of the cylinder, divided by J is conductivity times E, right? So this becomes S conductivity times E ds, and I'm taking E to be uniform, right? So this just equals EL over sigma ES, cross-sectional area of the cylinder, right? So E cancels with E, and I end up with the result that the resistivity in the circuit form of Ohm's law is L over rho S ohms. And this is an equation that you might have encountered. Clearly, R is proportional to the length. The longer the material, the more resistivity you have. R is inversely proportional to the conductivity. More conductive the material, the less resistance you have, and inversely proportional to the surface area. So if you have a larger surface area, you have more space, more area for the charge to move, so which encounters less resistivity, right? So R is inversely proportional to the surface area. Okay, and this is the resistivity in the form of Ohm's law. This is how we tie Ohm's law to the circuit form of Ohm's law to the field variables. Right? It turns out that V over I is really a constant. Turns out to be a constant that does not depend on the field. So Ohm's law, even in circuit form, is true. Okay. So now we're done with Ohm's law. I wanna discuss a consequence of Ohm's law, uh, which is called Joule's law, right? So this is, so I'm going to talk about power dissipation. I think, like I think I mentioned it last time. A major facet of Ohm's law is that it doesn't only relate current to electric field intensity. It indicates that energy needs to be dissipated in the material because of the way it models the drift of the charges. So the charges, instead of accelerating at a constant rate due to the field, they constantly lose their energy by hitting atoms in the structure, and then losing their energy and then accelerating again, effectively leading to a steady flow of charge. So that nature of this behavior by itself indicates that energy is constantly being lost in the material. And to quantify that energy, we need to study Joule's law. So power dissipation and Joule's law. Okay. So from mechanics, what is power? Power is the rate of change of energy with time, right? Power is energy over time. Like how much energy is flowing into point of space with respect to time. And for how does it relate to force? Like, let's say, let's forget about power now. Let's say I have force, and then force is multiplied by displacement. So let's say there's a displacement dot the force, that gives me the work, right? But we said work is energy, so we said power is energy over time. So I need to divide this by dt to get power. So this is energy, and this is time. So this gives me power. I bring the dt in, so I have dl by dt, which is velocity. So power is force dot velocity. If there's a particle that has a certain velocity that exists in a force field, the force dot the velocity is the power, right? For electrostatics, this is in general, this is true for any mechanical system or any physical system really. But for an for an electrical system where we have an electrical field, we know that the force is Q, the charge of the particle, times E dot V, right? So this would be the form of the power for dissipated due to movement of a single charge, right? So we want to move away from single point charges to a charge distribution. So let's look at our space. We have our space, and we have a volume, a small volume element, dV. How many, let's say I give you a number n. This number n is the number of charges per unit volume. The reason I'm doing this is I want to figure out what I don't want to I want to find out what if I have a J field and an E field. I want to find out what is the power dissipation at every point in space, right? Without using the V, getting rid of the V. You know, if I have a resistor, the power is dissipated not in some point in the resistor, it's dissipated everywhere where the resistor exists, at all points of the resistor, right? So if I give you n as a number of charges per unit volume, then a volume dV will have N. So this is charges per right. So N has units of Coulomb per meter cubed, right? It's number of charges. Oh, sorry. It's a number per meter cubed. It's not a number. It's not Coulomb. Okay. So it's a number of charges per unit volume. So if I give you dV, the number of charges inside that volume element is going to be N dV. Right? So N is number per unit volume times the volume gives me the number of charges within that volume. Okay. Right. So what is the power dissipated at a certain point, at a point then, let me call it, what do you call it? Let me call it dP, okay? dP. So this is the power dissipated in this volume, okay? So we just use this same formula, right? So this is going to be N dV. This is the number of charges in that volume. Q times Q to give me the total charge, right? And each charge is going to be affected by the electric field E dot V. Let me rewrite this. So this is going to be N Q E dot V dV. Okay. What is NQV? Remember? J is NQV, right? So NQ is the number of charges within the unit volume, right? That's gonna give me Coulomb per meter cubed times the velocity, which is meter per second, right? That's gonna give me Coulomb over second, which is ampere over meter squared. Right? I mean, you have to go back to the previous lecture and you'll see that we derived this already. So it is the amount of charge in the unit volume times the velocity gives me the charge density. So this is NQV is the charge density. So that tells me that the charge dissipated in the volume of space of this small differential volume of space is J dot E, right? dV, watts. Okay. So this is okay. So J dot E is the power density, right? Because J dot E times dV gives me the power dissipated in dV, right? So J dot E is not power. J dot E is power over meter cubed. Then I multiply it by dV to get power. Right? So what is the total power then that's dissipated in a volume of space? It's just the integral of this power density. So the power density is E dot J dV. This gives me watts, right? And those are the power relations. This is the Joule's law, actually, right? So let me write it here. So this is the total power dissipated in a volume of space, and then what I call the power dissipated at a point, P, let me call it small p, d, that's, or power density. So d stands for density, right? So this is the power dissipated in a volume, v, and then the power density at every point of space is going to be E dot J watt per meter cubed. This is what every point in space is losing in energy, or is what this is how every point of space is losing energy essentially, or power is flowing in every point of space. That will tell you how every point of space is heating up, right? Or not space, sorry, the material, right? So I can rewrite this as, of course, I know G is epsilon E, right? So I can rewrite this as sigma E. So I can rewrite it as sigma E dot E, which is sigma E squared. So that's one expression. Or I can rewrite this as E being J dot J over sigma. So that gives me J squared over sigma. And this is another expression for the power density, so it's the watt per meter cubed. Okay. So this is the total power, and this is the power density at every point in space, which we can find from E using this formula, or find from J using this formula. And this is Joule's law. How does it relate to the circuit version? Right. So the circuit version is simply P equals VI. Can we show that we can get P equals VI from this? Yes, we can. We use the property that if we take a cylinder, this is dl in this direction, this is total length L, right? And this is S, let's say, okay? And then we have the electric field inside and J inside, right? So the power we said is the volume integral of E. So let's assume we know E is in the direction of J in this volume. So let's assume this volume is small enough such that E is uniform and J is always in the direction of E, right? So I can take the dot product, and in general for conductors you can take this dot product to be just the magnitude of E times the magnitude of J for typical materials, because J we said always going to be in the direction of E, right? So I can take this integral as just E times J dV, where E is the magnitude of E and J without the arrow is the magnitude of J. So this makes sense, right? This is correct because E and J always share the same direction. We can just take the dot product as being their magnitudes. Okay. Now the key concept here is that I can divide this volume integral into two integrals. I can divide it into a surface integral over this surface S, and then a line integral over L, right? So I can divide it into this double integral EJ, right, over ds, and then I take this whole thing and I integrate it, do a line integral over dl. Okay. Now the key thing here is because over the surface E is constant, I can take E out. I end up with this, right? So I took E out. What is this surface integral of J across the surface? That's I, right? I can take I out now, and then I have integral over L of E dl. What's E dl? That's the voltage, right? This is V. So this is equal to IV. And this shows that the circuit form of Joule's law follows precisely from the field form. Okay, so this is Joule's law. How does, okay, what's the other big theorems from theory from circuits that we can relate also to the field formalism of the steady state current? Well, to two things. We can talk about continuity, and then we can talk about Kirchhoff's current law. Kirchhoff's current law is a big one, and it should follow from the current treatment that we have for current, right? To describe Kirchhoff's current law, I first have to talk about about continuity. What do I mean by continuity? Right. So the basic tenet that perhaps we didn't discuss this at the beginning of last lecture, but I'm assuming everyone knows this already, right? Charge is conserved. Like momentum and like energy, charge is one of those physical, unlike mass, charge is one of those physical quantities that is conserved. Forget I said what I said about mass. Mass is mostly conserved, but sometimes mass can turn into energy, as was discovered, you know the famous formula E equals mc squared. So it's possible to turn mass into energy under certain conditions, right? But charge is absolutely conserved. Yeah, I mean, charge is like energy and momentum. If someone tells you, hey, there's a physical phenomenon that does not conserve momentum, you should instantly know that it's a bunch of hooey. Okay, so charge is conserved. So what does that mean? Well, let's say I have a region of space and I tell you, hey, at the surface of this region, there's a line here and there's a current flowing out from this region. What does this tell you about the total charge in this region? How does the current relate to the total charge in this region? First off, because charge is conserved and current is flowing out of this region, and I'm not showing you any current flowing in. I'm telling you, hey, this is the only current that's happening. There's no current flowing into the region, right? That means that because current is flowing out of this region, and because current is the flow of charge, and because charge is conserved, the total charge inside this region must be going down, right? So current, the amount of charge going out, this is Coulomb per second, should be equal to the same amount of current, the same amount of charge that this region is losing, right? So current should be minus dq by dt. So if there's a positive current going out, this charge should be going down, right? Because the charge in the region is being depleted by the current, and the rate of change of this total charge in the region minus should give me the current flowing out of the region, right? So this is called continuity, and this gives rise, this results in what's called the continuity equation, which we will derive. But it essentially falls back to conservation of charge. If there's a current flowing from a region out from a region, there's no other current coming into the region. I mean, the charge that's in the current should be coming from somewhere, and this should be coming from that region. So the charge within that region should be going down. There is no infinite source of charge that's within space, right? So this gives me the continuity equation, which we will derive in integral and differential form. Okay, so what is Q? Q, the total charge in the region, is just the volume integral of rho v dv, right? This is the charge density within this region, rho v. That's what the total aggregate Q is. What is I? I, we said, I mean, we defined I here to be this, right? So I, let me write it in terms of the integral. So it's going to be minus d by dt volume integral of rho v dv. Okay. cool thing I can do with differentiation is an integration. I can plug into differentiation into the integral. I can swap the order and nothing will change. So I can write this as the volume integral of minus d by dt. Oh, why is this, by the way, a partial derivative? When I take it here, here it is not a partial derivative. I'm forgetting what is this, you know, standard derivative, yeah, full derivative, whatever, I forgot. Anyway, so this, because q is a function of one variable, q is only a function of t, right? Here, rho v is a function of t and of the point in space. So this is a function of t and space. Hence, we do a partial derivative. Oh, this is an ordinary derivative. So this gives you an ordinary differential equation, while this gives you a partial derivative equation, differential equation. So this becomes a partial derivative because rho v is a function of time and space, dv. Okay, and this is I. Okay, I have an integral on the right hand side. I want to get an integral on the left hand side. What's I? I is an integral over a surface of j ds, right? The current density integrated over a surface gives me the lumped I, right? This equals v minus d dt rho v dv. Okay, so I have a volume integral on one side, a surface integral on one side. I cannot compare the integrand because they are different sorts of integrals. But what I could do is I can apply the divergence law, right? So if I have a surface integral, I can relate it to, oh, this is a closed surface. Why is it a closed surface? Because I'm studying this case where I have a current coming out of a closed, enclosed, finite volume of space. So this finite volume of space is going to have a closed surface at its boundary, right? Because this is a closed surface, I can relate the closed surface integral to the volume integral inside the closed surface using the divergence theorem. So here I use divergence theorem. So all the math that we spend a long time studying in chapters 1 and 2, notice how it always comes back, and it's very useful to get all those results that we're getting. Okay, so using the divergence theorem, I turn this into a volume integral v divergence of j, right? So this is equivalent to that, right? According to the divergence theorem, dv equals the divergence theorem, the volume integral of minus d by dt rho v dv. Okay, and this gives me the continuity equation. I compare this to this, I end up with divergence of j equals minus rho v over dt. And this intuitively makes sense if you have some volume in space, small volume, infinitesimal volume, where there is a divergence. What does mean there's a divergence? Meaning j is going out like this, right? That's what it means to have a divergence at a point, right? So since the current is flowing out from this volume, naturally the charge density in this volume should go down. And yeah, the rate of change of charge in this volume is going down. So the charge in this volume is going down by that rate. The rate of it going down is a function of j, according to this formula. Now, if we are in situations where the charge in a volume is replenished continually, so if charge is replenished continuously, so you have a small volume and current is going out, but current is also coming in, so that the charge in that volume does not change, then we have this equation, divergence of j equals 0, if rho v is constant, does not change with time. Okay. If rho v changes with time, we get this equation. If the rho v does not change with time, the divergence of J becomes 0, which makes J then, in that case, a solenoidal field. Okay. Typically, and in this chapter, we're focusing on steady current. Typically, steady current must flow in a closed circuit, right? Why must steady current flow in a closed circuit? Because if current is not steady, then charges are constantly changing in space, right? But we cannot have a situation where we have suddenly 1,000,000 coulombs in a certain point of space, right? So if we have a situation where charge does not change, and typically charge does not change because charge is conserved, that implies that divergence of J must be 0. What does it mean for divergence of J equals 0? That means J is solenoidal, meaning that J has no point source. J cannot have a point source like this. This is what it means for divergence of J to be 0. J does not have a point source. If J does not have a point source, that means the field J as a field, whatever it is, should always fall back and loop on itself. So the current should always go in a circuit. Current is always going to flow in a circuit because it's going to start somewhere, flow, and then flow back to where it started, solely because J, if rho v is constant, J is a solenoidal field. And in situations where we are not adding charge into the system, right? Charge is only flowing, like for example in a transmission line, charge is flowing from the generator to the load and then coming back, right? We're not creating new charge, and we cannot create new charge, right? If we have a situation where rho v is not constant, we will quickly reach a steady state where rho v becomes constant, because if rho v is not constant, charge cannot keep growing until it reaches infinity, right? We cannot deplete all the charge from where the generator is located and dump all the charge in your home. Otherwise, your home will be charged at millions of coulombs, and then you just die by exiting your house. You get zapped by the voltage differential. Okay. So this circular motion of charge, this discovery, that this statement that we made that J is solenoidal as a field, leads to, and that current flows in a closed circuit. This leads us to Kirchhoff's current law. This is the root cause of Kirchhoff's current law, right? And the Kirchhoff's current law can be observed by just taking the differential form, the integral form of this, right? So again, if rho v constant, right, I can take the surface integral of J dot ds over a closed surface to be 0. So if I have any volume, what does it tell me? That tells me if I have some J flowing in, let's say this is J flowing in, and some J flowing out here, and some J flowing out here. So this is J1, J2, J3, right? The integral of J dot ds, those surfaces here, in this that are bordering the volume, should be 0, meaning any incoming current should be equal to any outgoing current, or any outgoing current should be equal to any incoming current, right? What happens in circuits is that we take this surface and volume to be, we take the volume to be approaching 0. So we consider a node, and we consider the current lines coming in, and this volume is considered to be 0. V approaches 0, right? And this allows us to, and the J's coming in are all lumped as total currents, right? So so this is I1, I2, I3, and we end up with Kirchhoff's law, which is I1 plus I2 plus I3 equals 0, right? So this is sum I equals 0. Okay, this is Kirchhoff's law. Okay, now in the context of circuits, Kirchhoff's law is always true, right? Always true, even if the current is not steady. Okay, this, by the way, if rho v does not change within the volume, right? First, if rho v changes, that's a different story. But if rho v does not change, this is true always for steady current. Okay, that's the major difference between the field form of Kirchhoff's law and the circuit form. So this is true if rho v inside the volume does not change for steady current. If I have a steady current coming in and a steady current coming out. This is not true for time varying current. So this is not true. True for steady current, not true for time varying current. Why is it not true for time varying current? Because, okay, so yeah, so the point is that this, if the volume where the currents are coming in and leaving is big like this, then when the current is steady, yeah, Kirchhoff's law applies. It's true. I mean, the total current coming in equals the total current coming out, right? If the current is not steady, meaning the current is time varying, then Kirchhoff's law in general for this, like big volume and the current flowing in and flowing out, is not true. Why? Because it's possible, if we have time varying currents, it's possible for us to have some accumulation of charge inside the volume, and then later, which won't go on forever, then later we will have some depletion. So you'll have accumulation, depletion, but on average, there won't be any accumulated charges over the long run, because whatever we accumulate, we later deplete. So that scenario is possible. So that means that Kirchhoff's law is not true in general for this case. However, if we take the volume to approach 0, then in a 0 volume, there cannot be much accumulation of charges, if any at all. Actually, nothing can accumulate in a 0 volume, right? So only in that idealized context where the currents, there's no current densities, the currents are all lumped into a line, and then the volume is lumped into a node that has zero volume, of course, then only in that case is Kirchhoff's law true, right? So Kirchhoff's current law is true for this scenario, whether the current is steady or time varying. Is true in this scenario only if the current is steady, right? If it's time varying, it's not true. So that is the takeaway. Okay, that's Kirchhoff's law. Okay, so notice sometimes when I'm talking about J, I'm looking at J as a field. Right? It is something that's vectorial, that's distributed in space. So I mean, in a similar way where we could look at rho v as fields, right? Charge distributions could be with that are distributed in space rather than point charges could be envisioned to be like scalar fields, right? It's kind of like any other scalar field. It's something that's distributed in space, right? So it's like a scalar field that generates the vectorial field E, for example. So I mean, we could also look at J as a field, and then we ask ourselves, what are the axioms that govern J? Right? So we want to build axioms that cover J, that describe J based on the axioms that we already know for electrostatics. Those have to be new axioms, by the way, because I mean electrostatics assumes that nothing is moving, right? So with steady current, we are assuming there is some steady movement. So we want to build new axioms that are based on the electrostatic axioms, right? And how can we build them? I mean, it's easy. I mean, we can just use J equals rho E, this empirical relationship to guide us on what the axioms for steady current need to be, right? So this is, I'm trying to find the axioms for steady current. If I steady current density, if I consider current density to be a field, what would its axioms be based on the results that we got so far, right? So let me remind you of the electrostatic axioms. They are rho E, sorry, divergence of E equals rho over epsilon, curl E equals 0. So I wanna utilize those, right? First off, for steady current, we said there shouldn't be any charge accumulation, right? Charge should not be accumulating, right? So divergence of J equals 0, right? So there can be charge accumulation, but delta rho v over delta t equals 0, right? So this is one result that we got for steady current. This result, right? If rho v everywhere is constant, so what we are envisioning is now we have our established electrostatic three-dimensional space in which the only thing that lives in that electrostatic space is charges that are constant and they do not move. That's one. And then well, that's it, you know, and then those charges are the sources of the electric field, right? So this is the picture that we had in the electrostatic field that exists in space. We want to now add to that picture, we want to allow steady currents. So this is going to be the electrostatic picture plus steady currents, right? And the one thing we discovered about steady currents is that they flow in a circuit, because if they are not steady or they do not flow in a circuit, they would tend to accumulate charge. So that gives us the first postulate for steady currents, is that divergence J equals 0. So this is the first postulate, modeled on the first postulate of electrostatics. Okay. So this is this new thing J that represents a steady current. So this is steady current postulates, right? So in addition, in a space where in addition to electrostatic charges, fixed charges in space, there also exists a steady current. In addition to the electrostatic field postulates, we'll have steady current postulates. The first one is that the divergence of J equals 0. right? And then the second one relates to this one, right? So curl of E is 0, right? So curl of E, instead of E, this is instead of E, what's E? I use this formula, J over epsilon, J over sigma. This is postulate 2. Okay, the curl of J is 0 and the divergence of J is 0. Now I kind of like cheated a bit. Why is it okay to use an electrostatics formula for a case where we have moving charges? This is kind of like a tricky point, but the reason is that even the reason is that this equation is true for both electrostatics, and even if the steady current exists, this equation is still true. Okay, so I can use it and I can just plug in instead of EJ over omega, right? The big reason is that because a steady electric current generates a magnetic field, it does not generate an electric field. That's the major reason. But we can take it for now as postulates. So for the purpose of specifying the postulates, we can, that's the point of postulates. You can just lay them down as postulates without proving them, right? Axioms. So those are the electrostatic axioms that describe what the field exists. If in space there also exists steady current, those are the axioms for that steady currents. So both in such a space where we have both a steady current and fixed charges, both axioms hold. So the electrostatic axioms hold, and we can use them to calculate the electric field, and the steady current postulates hold. Okay, and then later on we can use the steady current to calculate the magnetostatic field, but we're not there yet. Okay, what do those two equations tell us? Those two equations tell us that J as a field is irrotational, its curl is 0, and it's solenoidal. Okay, and then as in any vector differential equation, there's always going to be the integral form. So this is the differential form. There is also the integral form, which I'm going to write down. Divergence of J is 0. The integral form is this, right? Closed surface J ds is 0. And then the integral form of that is that the line integral, closed line integral of J dot dl over any closed contour C, right, over sigma is 0. I don't need the sigma. I could have really forgot that sigma, right? It's just I can take it to the other side and it becomes 0. I would keep it because what if I have a problem where I have materials, different kind of materials with different conductivities, okay? So what does it mean for a field to be solenoidal? That means it doesn't have a source. So for a steady current, there is no source. There is no point in space where that current is flowing out, right? And the lines all close on themselves. The current flows in a circuit, closed path. Okay, so I mentioned that you could use this in cases where you have materials with different conductivities, which brings up the question of interface conditions. Remember when we talked about interface conditions for the E field, if we have two materials with different permittivities? Well, the equivalent problem is what happens to J as it crosses the interface between two materials with different conductivities. This is J1 and this is J2. We will discuss this next time, right? And that will conclude chapter 7, and then we will solve some problems. and then we will move on to magnetostatics. Thank you.